Okay, good morning everyone. So we will start to continue to talk about some basic definition and fundamental knowledge related to reliability. So last week we have already mentioned, for example, what's a definition of the reliability related to the specific condition, how we define the values, and also the time-dependent characteristic. So today we will talk about what's the difference between the value modes versus the value mechanisms. So value mode, which is the recognized electrical symptoms by which value is observed. So it's something that the electrical result that we can observe that something happening, that the device has been reached a condition as a value. For example, if you look at the gate lead current versus time, and then last week we have been mentioned that there's a very famous reliability issue, what we call the TDB, where in the beginning we see the current slightly decrease, and after a certain moment we start to see the current increase, which has a certain dielectric breakdown in this region. So therefore this is a electrical symptom for the TDB reliability issues. So that's our value modes. And in addition to this one, there are some other value modes. For example, a short or open circuit, electrical open device input, increase current are the all modes of the electrical values. And also, each mode could in principle be caused by one or more different values mechanism. So that means that the same value mode could be possibly caused by the different combined mechanism. For example, if you look at the very typical case where we have the MOSFET here, which this is a source, drain, and gate, and we have the dielectric in below. And in addition to typical structure, like here we have a gate, source, drain, and normally we also need to connect this electric pad, this electrical signal to the outside. So normally we will further have the interconnection line that try to allow us to have the signal reach to the outside. So we will have the interconnection line in each contact. And between this interconnection line, normally we will also have the dielectric, which is a passivation, try to isolate the electrical signal from each interconnection. So we need to make sure that this and this electrical signal are well isolated. So we will have the insulating material here. We will also have the insulating materials here. But when we try to operate the device, and at a certain moment we observe a certain very high leach current, and this high leach current can be caused by one or more different failure mechanisms. For example, in this case, in this structure, if we both consider the front end and back end, there are two possible mechanisms can be happen. And the first one is something we consider as front end gate dielectric reliability, where we might have the TDDB in the gate dielectric region. So this can contribute as a one failure mechanism. On the other hand, we might also suffer the leach current between the different interconnection line. Once reach to the different interconnection line, we also have the chance that the device will have the very high leach current, because of now our drain and source interconnected are short together. So in this case, we might have another mechanism where is TDDB in the passivation layer. So when we observe the failure modes, as shown here, that not only the one mechanism can contribute. In fact, actually several different failure mechanisms can all contribute. In the end, shows the same high gate current after a certain moment. So it's very important that when we consider the failure mechanism, we need to think in the very comprehensive way, because of not only focus on the one region. Sometimes we have to consider that the other region might also induce a degradation. So that's a difference between the failure modes versus the failure mechanisms. So the failure mechanisms are the specific microscopic, physical, chemical, metallurgical, environmental phenomenon. Or process that can cause device degradation or malfunction. So this could be the certain environment, certain phenomenon, or certain process in the end will cause that we can see the device characteristic shift, and we can see that in the end the device is not be able to function. For example, the open circuit. So open circuit of an interconnection could occur because of the several possible mechanisms. One is a corrosion. Second is a too much current flow. So therefore, the open circuit, which is failure modes, and the corrosion, and also the high current flow. These are the mechanisms. So therefore, it's very important that when we try to look at the device failure, try to understand the degradation, in the end, we need to understand what would be the failure mechanism that's responsible for this failure mode. Because if we can understand the failure mechanism, that will highly help us to further improve. If, for example, if we know that the failure mode here, the open circuit, is due to the very high current flow, then we have to think about that how to reduce the current density. For example, you increase the interconnection line width or reduce the operating current, then that can highly improve the reliability of this interconnection line. So another very often see the failure mechanism is a high electric field dielectric breakdown, which is another failure mechanism that very often see not only in the pure gate bias operation, sometimes in the very high drain bias, or even sometimes for ESD issue, we also see the gate dielectric breakdown is always very often happen failure mechanism. Okay, then we have to first to continue to understand that what does this reliability mean to us, and then first of all we have to be aware of that in general, no matter whether in the semiconductor or in the general things in our life, actually we can consider that there are two states of the one particular thing. This is not only for the semiconductor device, for all kind of product, even for human being, we have the reliable state and also the fail state. So in general, the failure consists of a transition from reliable to fail states. That's why we need a certain time to accelerate. We need a certain time that this process can be happen. So therefore, this is why the reliability is always related to the time dependent. So the failure always begins through a time-dependent failure. Always begins through a time-dependent movement of the certain physics-based or chemistry happen. For example, can be the movement of the atoms, movements of the ions, or movement of the electronic charge from benign state in the device or component in the end to the harmful side, from the benign side to the harmful side. Benign means the good, from the good beginning in the end leading to the condition that will damage our device. And in here, the atoms, ion, or electronic charge, especially the electronic charge here, we normally refer to the issue as a trapping, because we have the charge in somewhere that we don't want, and then in the beginning we don't have a charge here, but after a certain while we have a charge in a certain place, and then that will cause a trapping, and in the end the trapping will cause a lot of instabilities. For example, one of the well-known issues for the reliability, if you look at the typical MOS structure, as we already illustrate, this is a source drain gate and below gate, which is a dielectric. And then we all knew if we try to apply the certain bias after a certain moment, once the bias is larger enough, we might start to have the inverted electrons in the channel. So that's a two-dimensional schematic we are looking from the device point of view. But to further understand how this bias will influence the electrical potential inside. Normally, we'll consider to have the cut line here, and then based on this cut line, we can draw the band diagram. So from the top to the bottom, which is equal to the schematic from the left to right. So in the beginning, we have the substrate here, where this is a silicon substrate. So this is a region. We have the substrate, and then if you have been following the semiconductor physics and device, you should know that we have the concept what we call the band gap here. We will also talk about band gap in the next chapter. So in the case with a band gap, so we can consider the length of the conduction band and valence band, and then in between the conduction band and valence band, which is normally we call as a band gap. And then beyond, this is a band diagram for the substrate, and beyond substrate, then we start to have the dielectric, and as you know, dielectric, which is insulator. So if it comes to the insulator, normally we have the large band gap compared to the silicon. So this is a typical case for the SiO2, where is a silicon dioxide here, and then on top of the silicon dioxide, we have the metal, and because of metal, which is the gate is a metal, and metal there's no band gap. So normally we only plot the one line to describe the metal. This is our gate metal. And now we have to consider the case where we start to give the positive gate bias. Once we apply the positive gate bias here, because if you try to spend a time, a little bit study about the Poisson equation, you will always know that the bias and then the electrical field potential always has certain minus characteristic, which means that we apply positive gate bias. That means our band will be pulled down. And then also we have been already knew that where our gate bias is larger than enough, then we start to have the inverting electrons in the channel, which is just below the dielectric. That means we will start to expect we have the electrons here. This is our inversion electrons. But on the other hand, you have to imagine that this is a negative charge. This is a positive bias. So in anyhow, this negative charge will be tried to attract it and inject it to the gate dielectric, because we apply the positive gate bias here. And therefore, we can start to expect this electron will try to be injected inside this dielectric. But if unfortunately we have a certain defect in the dielectric, for example, we have the loss of a defect in the dielectric, these are the defects. So therefore, these electrons, once being applied the positive gate bias, the electron will be injected into a dielectric, and because we have the non-perfect dielectric where we have lots of defect inside, so therefore we can expect these negative electron will be captured by these defects, right? I think so far this phenomenon is very straightforward. We don't need a very complicated equation. That's just use some high school physics. I think still so far can easily understand. So once we have the defect here, and because of electrons is injected from the substrate to the dielectric, so therefore the defects can capture the electron. And this phenomenon is what we call as a trapping. So certainly certain electrons is being trapped inside the dielectric. That's why we call this as a trapping effects here. And because of this trapping effect, you can imagine that once we apply bias, this electron being injected inside, so we start to have the defect that will capture our electron and cause a trapping effect. But sometimes we will also bias at the 0 volt, because you will not always turn on your transistor. And then once you bias at 0 volt, so this electron at this place might also will skip away back to here as well, because there's no positive bias to keep it attracting them. So sometimes they will be jump back, and this is a phenomenon that we call the detrapping. So sometimes we can also expect this electron will be coming back to the channel, which is usually we call the detrapping here. And because of this trapping and detrapping dynamics, and that's related to our bias and temperature, so that's why this phenomenon is we call the bias temperature instability. And also this is mainly the trapping probably related to the interface. So sometimes we also consider not everything is related, but some of the reasons related to the interface trapping. So this is a huge topic that we will also talk about later, but this just give you a certain sense that the ones we have electronic charge from benign size move to some harmful size. In the end, we create a certain unstable characteristic. So if these auto electrons accumulate in sufficient numbers at a harmful site, then damage will happen. So that's why we use this example to describe that how this electronic charge can be move out, where lead to the trapping and detrapping effects. So when we talk about the change from the reliable state to the failed state, then we have to first to understand what is the triggering condition for this change. So therefore we have to go back to the some fundamental. The first one is thermodynamic. So in general, reactions naturally proceed when energy is reduced. So when we talk about the transition from reliable to failed behaviors, so the energy of a reliable state always exceeds loss of a failed state. So fundamentally, a sense that has a reliable state always has a higher energy compared to the failed state. So in nature, it is naturally happen that everything will gradually move from reliable to the failed, because the things want to find a way reach to the minimum energy. So the energy of reliable states exceeds those of a failed state. The process must proceed at a certain rate. Similarly, in the chemical system, two conditions are necessary in order for reaction to readily proceed at a constant temperature and pressure. So when we talk about reliability, it's not only like the new knowledge you will see in the semiconductor. It's original in the very basic chemistry reaction related to thermodynamics. We already knew that the reaction will naturally happen from the reliable to the failed state, because reliable state has a high energy, and then the system wants to reach the minimum energy. So the thermodynamic requires the energy of the system be minimized. So the system always, if you look at the whole system, the energy always want to proceed in the minimized effort, which we want the energy be minimized here. And therefore we can define, this is a equation mainly coming from the thermodynamic field, which we have the term that's called the Gibbs free energy, where this is a measure of the chemical energy associated with the atoms or molecules here. So we can define the delta G, which is equal to GF, the final state, minus GI, the initial state. So in general, the delta G is always negative. So GF is free energy of the final state or failed state, and then this is a GF, and GI is the initial or reliable state. And the delta G would like to achieve the most negative value as possible. That's in the case where we can achieve the state that we call as a thermodynamic equilibrium. So from the chemical energy, from the thermodynamic point of view, we also already have this well-known equation that we call the Gibbs free energy, and this delta G will always want to be the most negative value possible. That means that everything will always want to move from the reliable state to the failed state. And also, if you try to go deeper for this thermodynamics for the material science, I think you have it already. There are some of you are from the material science background, so you know this better than I knew. But in here, we just try to borrow some of the concept from the other field, just let you know that these things is happening, not in the semiconductor, in all kind of material science. So there are two primary ways that system can be spontaneously lower its Gibbs potential by either decrease its delta H, which is enthalpy, or by increase in delta S, which is entropy. So let's look at some of the very simple case, like the left bottom figure. These are the two examples of a spontaneous change can happen, and they both try to reach the same objective. These two examples are spontaneously change, and they want to reach the same goal, which is a lower Gibbs potential. So, for example, the first one is that if you try to split lots of oil, as you know, you try to split lots of small oil in the water, in the end, the oil will come to close. We try to get in touch with the other, and then in the end will become like in this one. And this is because of the condition can reach the delta H decrease. But on the other hand, if you try to have the alcohol in the water, and then they will spontaneously to split out as a lots of a small alcohol in the water, which is delta S increase. So this is from the very simple case that we can consider as a process of this one is decrease enthalpy, and this is increase the entropy. This is one example how this Gibbs potential try to achieve the lower potential as possible. On the other hand, if you look at this example is more related to our case. So we have the two metal, one is the anode, one is a cathode, and being separated and with a certain dielectric. And now we apply the bias here. We have the positive bias, we have the negative bias, and for sure inside this dielectric we will start to have the electric field that will have the polarizations. And in this case, the Gibbs potential is increased because we apply the additional bias, and then fundamentally this Gibbs potential is increased, the energy inside is increased. But in the end, this system will want to achieve the lowest Gibbs potential as possible, which is one, there's a short happening in between the anode and cathode, and therefore this Gibbs potential will decrease. So now you can understand that why reliability is always happening, because in the end the system wants to achieve the lowest Gibbs potential where this is the case, and then in this case we got the fail, we got the degradation, we got the reliability issues. So Gibbs potential is defined in such a way that any spontaneous change in the Gibbs potential can occur only if the change leads to a reduce in Gibbs potential. So that's another example. That's just let you know that the condition for the change is not possible to avoid, because of from the fundamental we already know that this is happening, but what we have to do is we have to make sure that we can slow down this process, we can try to minimize this process. Okay, so the work done on system material against a conservative resistance force tends to increase the potential energy of the system materials. So therefore, the work can increase the Gibbs potential. However, the increase in Gibbs potential makes the system material more unstable. Because of the Gibbs potential prefer decrease in a potential, not in an increase. So therefore, a material in the stress state. The stress state means that we try to give a certain bias. For example, we apply the bias and temperature in one material. And therefore, we can foresee there's a spontaneous change. And the change here means a degradation. In the stress material is expected since the degradation can lead to a reduction in the Gibbs potential and free energy. So that's why that these things, as I say, that we cannot avoid. So the only things we need to do is try to minimize and try to find a way to slow down and try to enhance the certain robustness of the one material, or try to find the best condition, bias condition that will not lead to accelerate this process. And the second requirement, which is related to the kinetic. So once the thermal reaction is thermally dynamically possible, it must proceed at a certain rate. And this rate is proportional to what we call the Maxwell-Boltzmann factor, also known as the Boltzmann, or even better known as Arrhenius factors. That's according to this following equation, where our rate is equal to constant exponential minus delta G over RT here. And delta G here is referred to as activation free energy. Because of this equation, whenever degradation is thermally accelerated, and therefore this equation is one of the most equations that we can describe the temperature dependent acceleration for this degradation rate, because we have the temperature here, so we can understand the rate versus temperature, but also versus this certain free energy. This, because in the end we knew that the things is always happening. We have the degradation from the reliable state to the failed state, and then we can foresee that there's a certain rate happening between the good to the bad, and therefore we want to estimate this rate. So that's why we come out this equation, and this rate also based on this equation tells us that the rate is related to these two factors. One is what we call the activation energy, and also this equation tells that the rate is related to the temperature. So now we also, because this, when we talk about this equation, this is equation we borrowing from the certain chemical reaction. So we need to go back to, again, to understand fundamental related to the chemistry reaction, where we talk about here is a diffusion in solid. So diffusion in solid in general considers chemical reactions, and when we try to describe this chemical reaction, then we have to come up with a certain way as shown in here. If imagine that we have the crystal structure where we have the lattice, we have the atoms arrangement like in here. This is in the very periodical lattice arrangement. But now, if we want to see the atoms move from the one side to another, two conditions must be fulfilled. The first one is we need to make sure that there is an available site. So for example, if there is atoms want to move from here to the right, the first condition that make sure this process can be happen is we need to make sure that there is a vacancy here, right? So if we have the vacancy, that means the empty place, then these atoms possibly can be moved. And second, the atom must possess sufficient energy. To push your atoms aside in executing required jump. So that means if these atoms want to move from left to the right, this atom will has to overcome the situation where these atoms will very closely with the other lattice, and then these very close will create the huge barriers here. And therefore we need to make sure that these atoms can have sufficient energy to push the atoms aside and then try to execute this required jump. So this, because of this place where these two lattices, these two atoms are close, and then this is a region where has no atoms, and this is a region where has atoms. So if we try to draw the energy between from here to here, we can expect the region where we have the two atoms in between must be the region where has a high energy, and the region where we have no atoms nearby must be the region where we don't have the energy. And now if we try to apply, if we try to want to see that one atom can be moved, so that means these atoms must also possibly to move to the right. That means that this atom must have the sufficient energy to move from here, jump to here, right? So this schematic can be also being understood from this energy barrier point of view here. So the rate of diffusion and chemical reaction are mathematically expressed by the same Boltzmann type of formula, where as shown in here, and then the D here, which is diffusion. So anyhow, I think the conclusion here is not surprise for us. This is a very basic chemistry reaction, and then we can foresee that lots of the reactions always have the temperature and certain energy related dependency, which is shown in here. The diffusion equation is also the same, correlated with energy, with temperature as well. So the rate of the diffusion and chemical reaction can be expressed by here as already shown. For simplify, now the delta G is replaced by the relevant activation energy. In this case, we call as ED. And both D0 and ED are dependent on the nature of diffusion metric and specific paths taken by the atom. And value D as a function of temperature for atomic diffusion is in semiconductor, metal, and oxide. That can be considered in the different case, different material. So finally, we can conclude that we can follow the same concept, and then in the field of the physical chemistry, we call this as Arrhenius equation, which is a formula of the temperature dependency of the reaction rate. This is proposed by this researcher Arrhenius in 1889 here. So this reaction rate is important because of also we can further consider this reaction rate as a temperature dependency of the value rate. So, Arrhenius equation is used to model the temperature variation of the different coefficient, population of a crystal vacancy, creep rate, and many other thermally induced process reactions. So, as long as there's a temperature induce a certain process reaction, certain degradation, we can always use this Arrhenius equation, try to modeling this temperature dependency. So there are the two different kinds of this Arrhenius equation that we can use in the different scenario. And the first one, the K is equal to A exponential minus EA over RT. And here K is a rate constant, and the EA here is activation energy for the reactions. But now we consider the R here, which is a gas constant. So this is the equation we use to describe the gas molecules. So which is something that we are not interested in. But in the case we are interested in the semiconductor, we just slightly revise this equation. It's still the same. K is equal to A exponential minus EA over, but now we have to put the K here, which is EA is activation energy, but the K is a Boltzmann constant for our case where we want to understand for the case in the semiconductor. So now we will slightly revise this equation and put as a certain constant that more fitted for our semiconductor analyze purpose. So now back to the goal, that how we actually leverage this very powerful arenas equation. So we can go back to the one fundamentally concept how we do the acceleration testing. So in the previous lecture we had mentioned that if we want to try to understand the one product lifetime, for sure the first thing we come out is we will buy this semiconductor at the room temperature at the one particular condition, for example VG equal to 5 volt. But fortunately our devices are very robust, so if you try to buy it at the VG 5 volt at room temperature, you will take 5 years, right, to see the degradation, to see the malfunction of our product. So therefore we have to use a way what we call the acceleration testing, and the concept behind is also very simple. As we knew, thermal, the temperature is always one universal factor to accelerate the degradation. So what we normally do is we just raise the temperature. If we raise the temperature at 150 Celsius degree, then we do again with the same bias condition. Then now we can highly accelerate this reliability testing process, because now we can see our product will show a certain degradation, just need 1,000 seconds. So that's a goal. That's a goal for doing the acceleration testing, because we want to accelerate the whole process. The 1,000 seconds is something, the testing we are able to manage. We are able to execute it in the lab, in the company. But then how do we convert back to the 5 years? Because in the end, we still want to understand the room temperature characteristic, right? So that's why we need to leverage this activation energy, because we have this activation energy EA. Because we have this activation energy that gives us a way to estimate the temperature dependency of this acceleration rate. So now we can use this EA and convert back to a room temperature, and finally we can know what is actually the lifetime for our product at the room temperature. So this is the very often used procedure in the semiconductor world, how we actually use a more effective, efficient way to estimate the product lifetime. That's why the arena equation is very, very important, that you will see very often that in the semiconductor literature, even in the product data sheet, even your customer will definitely ask you what is the activation energy for your product, because with the activation energy they can easily convert to the lifetime of your product in any different temperature. So let's just look at the one of the examples. This equation, to be honest, is with everyone's professional knowledge from high school till so far. This probably is just one of the most easy equation you have ever seen, because of you have been being asked to solve a lot of very complicated equation in the college. So let's just did a quick the exercise how we actually use this equation. So this equation is k equal to constant exponential minus EA over KT. And to have a more efficient way to extract the value of the activation energy, we just do the very simple mathematical tricks that we just put a natural log in the both sides. So we have a natural log K, which is equal to natural log A minus EA over K times 1 over T here. And here we just do some trick to rearrangement of this one, which is minus EA over K 1 over T plus a natural log A. Now we just put this equation as a natural log K as a Y, which is equal to linear function nx plus b, and we put the x-axis as a 1 over t here. So that's why if you start to have been asked to do some reliability testing, you will very often to see that when we try to extract the activation energy, we are very often plot this one, what we call the arenas plot, where the y-axis is a natural log, and then the x-axis is a 1 over t. And if you try to conduct the whole process with the 3 different temperatures, then you get the 3 points. And just do the simple linear fitting. And you get a slope, which is a minus EA over K. And then the K here, so we can use this simplified calculation to estimate the activation energy without very complicated process. And then the K here can be referred to any parameter that we want to understand the temperature dependency degradation rate. So the K can be threshold voltage shift on increase, IG increase, any one factor that you want to see the temperature dependency of the acceleration rate. So that's why the arena plus is very powerful. So this is also very very classical example that as being the undergraduate student for a while, you probably have learned a lot of the very complicated equation, the partial equation, PDF, complex vector, whatever you have been known a lot. But once we get to the real world, sometimes we want to simplify the case, and then the mathematics we always want to just try to validate our physics-based knowledge. But in the end, the one that really we need to hands-on calculating, sometimes just the equation simply like just this one. This is a very simple equation that we have been knowing since high school, but the most important part is the physics inside, because of physics give us lots of the different interpretation of our mechanism. So in the end, the mathematics is just a tool. Sometimes just don't feel frustrated that sometimes you probably have been struggling with all kinds of mathematical equation, but my experience tell me that mathematics just will be the tool, and then the most important is very important is the physics behind. In my class, not only this one, also the semiconductor physics and device. Sometimes I got a lot of students' suggestion that I should spend more time in deriving the equation. To be honest, I think nowadays with the help of AI, the deriving equation is not that important. The most important is to understand the physics. The equation derived just try to prove that the physics is correct, just like the case with the quantum mechanics, that you understand the quantum mechanics in the end, just try to illustrate the quantum tunneling. But we still have to prove the concepts correct, so that's why we introduce Schrödinger's wave equation, we introduce a lot of different cases. But anyhow, if you forget those equations, that's still fine, because in the end, for us, the physics-based understanding is way much important than the mathematics equation. And then for sure, I believe with your capability, all those equations you can read at home, understand at home, ask the GPT to explain to you. But the physics sometimes that you need to have a little time to finally understand it. Okay, so now back to our original questions. As we know that what we actually want to see is that the Alton movement, and then we want to understand that what happened if we want to see the one Alton's move, what would be the condition that can trigger this move. So if there's no driving force or no bias is not existing, the Altons will migrate with an equal probability. In the opposite direction, which means that you have a one Altons here. If you don't give any bias, this Alton will just randomly move left and right. But in the end, there's no net displacement. Of course, this is not the case we are interested in. We are interested when there is a driving force happen when we apply the external force. If we try to apply external force, we can also understand the condition that this external force can trigger how these Altons movement. So in the beginning, we have the Altons in this place. And we all know in the right hand side there's a vacancy, and as we already illustrate, the vacancy, the Altons here can be also understood that we have the Altons in this place. But if you want to see these Altons move to the right, there must be a certain external forces where we can expect this barrier energy, this energy diagram will be shown as here, that we have this and this is because of, sorry. And this is because we have the additional force here. And this additional force will lead to the different energy where in this place we have a delta G star, but in this one we have a delta G star plus delta G, and therefore this Alton side 2 has a low energy. This is the Alton in the side 2. So when a driving force exerted over the dimension A, the periodic array of lattice energy barrier will tilt, as shown here. So there's a tilt happen, and now the side 2 has a lower energy than the side 1. So that's why, because of this low energy, so now we can foresee the Altons can start to move from left to the right place here. So then the conclusion is the same, that the system will want to reach to the low energy, and because of the side 2 has a low energy, so we can expect that this Alton will be able to move to the side 2 from the side 1 with additional force help. So the rate between the side 1 to the side 2 we can estimate, which is R12 is equal to V exponential minus delta G star minus delta G over RT, and the same, the rate between R21 is V exponential RT minus delta G star plus delta G. So the net rate, which is equal to R12 minus R21, and in the end, this is a equation showing here, and this equation describes both chemical and physical change induce the diffusion of the Altons here. And then the velocity, this is a velocity. This is a velocity here, where we can define this one as this is a very simple calculation. Try to understand that the diffusion that cause the net rate here. Then we have to also introduce some basic calculation, because in reliability we define the several different terms that you will very often to see. The first one is what we call the mean time to failures, NTTF. Which is just to use an example, probably you will get more sense that if we consider the TDDB reliability, we have IG versus T here, and if we bias 3 different conditions, then you will see the condition 1 will cause a breakdown here, the condition 2 will cause a breakdown here, and the condition 3 will cause a breakdown at the 3 different time, which is T1, T2, and T3 here. So the mean time to failure, which is defined as T1 plus T2 until Tn over n. So that means in our considered case for TDDB, the NTTF, which is T1 plus T2 over plus T3 over 3. So the calculation is very simple. And on the other hand, we have another one, what we call the mean time between failures. That's we call the NTBF, which is T2 minus T1 plus T3 minus T2 until Tn minus 1 over n. So that's a NTBF here. So in anyhow, these calculations are very simple. I believe that we don't have to further explain what's the difference, because from this equation you can already understand the difference between the NTTF and NTBF. And also there's another one that we often very use is a median time to failure. So the median time means that the median, so that means 50%. So usually we call as a T50%, which is occur when 50% have failed. So that's we call the T50. So that means that when you try to do the reliability testing for a large amount of the product, if you have a 100 product, you test until the moment that you found out that there's a 50% of your product have failed. That's the time we call the T50. So mean time to failure, T50, which is very important because T50 sometimes the value very high, but in the end, the normal spec for our product, which is T1%. So what does mean T1%? It's a time when we test for 100 product, the time will reach for the one product fail. That's called the T1%. So that's exactly what we want. But sometimes T1% is still very high, but in the industry perspective, sometimes we need a T0.01%. So that means if you test for the 10,000, 100,000 product, the time to reach for the 0.01% is the time we call the T0.01%. And on the other hand, there's also very important timing factor. It's called the T63%. And later we will tell you why that we will be interested in the time to reach to the 63%. But in general, the goal is that this time factor is very important that allow us to use for the Weibull distribution. So when we later to talk about some statistics and mathematics, we will talk about the different distribution mathematics, and then we will talk about the Weibull distribution And at that moment, you will realize that the T63% is another very important time that we have to time to look at. So, NTTF used to describe or model physics value of times. On the other hand, T15 will mostly arise in the statistical mathematical analysis of a value distribution, not the T50, but also T63 is also very important. So with the equation of the NTTF, now we can start to estimate the acceleration factors, and then the equation is also still very simple. The acceleration factor, which is defined as NTTF at the T1 over NTTF at the T2. So just put the previous equation here, and then you can have this equation coming out. So let's just use a very simple example. This is AF is defined as a ratio of the degradation rate at the elevated temperature of the T2 relative to the low temperature of the T1. So for example, if we have the T2, which is 150 Celsius degree, and then we test the product where their NTTF is equal to 100 seconds. And then if we test at a 25 Celsius degree and the NTTF is 1000 seconds. So therefore, the acceleration factors, which just equal to 1000 over 100, which is equal to 10. So the calculation is very simple to estimate the acceleration factors. Okay, so we will take a break for 10 minutes and we come back at 11.
OK。那我想跟老师请教的问题是说，因为我们这边是最近有那2册那个 VTI 系列，对，那一样是希望透过这个2次equation去计算一些东西，但是因为我们是做9每年的元件，然后譬如说我给你看我们做的data，譬如说这是我一个9每年元件，它有2种界面处理，对，这个不同难度的东西，对，因为我们需要算它的 delta VTI，对，去套那个equation，对。那可是我这边有一个很大的一个困扰，就是说，因为在高温的情况下，我们的元件很明显有一个裂化的状况。对。就譬如说，你看它这个越来越变。对。那这种情况下，我算出来的 VTH 还是能够套到，因为那是equation。
所以你要找到一个 VTH 是在室温跟高温都同时是 consistent 的 VTH 出来方式。
对，那我现在跟老师，
因为这个高温的时候，它的这个 电流一定比较低嘛，这个是 mobility degradation 或者 content degradation， 所以它是 mobility， 它 drag current 比较低。
像我自己原本惯用的方法是用电流法去算我的电流费，可是我不知道是说在这种 case 的情况下，我应该用哪一种方法去萃取 BTM 会比较准确。
电流法，这样电流法可能会比较适合，你可能要试试看电流法，看算出来EA。
那如果说我这边像我这个是 PPT， 对，我算出来大概是这样子。那算电流法算出来，我觉得这个图形应该算是合理的一个图形。就是它上面的就是它的电流会越来越多这样子，然后下面的条件是比较好的，就是对于这个处理方法的预测是像是 NBTI 那边可能出现一个大的问题。譬如说我 NBTI， 那它的这个也是做不同的度，那也是用一样是用电流法，可是它这个图形变得额外的不一，看它
就是不同的机制，所以它在这个 SS region 这边有些是这样子，有些是往左。对，所以代表说你在 NBTI stress 的时候，可能产生了不同的 defect， 它会 damage。通常在这一块，我就认为是 interface， 那这一块是比较偏近这个比较深层，对，可能要思考一下，在这 NBTI condition 下面，它为什么会产生？例如说这个是 degradation， 跟这 degradation 它两种不同的机制。对，所以就有对你元件比较熟，就比较没办法直接判断，但是要思考一下，它为什么它的 shift 不是一个 error， 代表它是不同的机制。
所以这个可能有跟刚刚的PPT是另外一件，可能也有不同的一些，
有可能有不同机制，所以导致说它的 EA 会不一样。等一下我们会讲一下 EA， 基本上你会看到这个，你吹这边 EA 跟吹这边 EA 就会不一样，代表它是两种不同机制。
这样，什么叫做吹不同 EA？
没有，你这个温度嘛，这是变温嘛，所以你说你用 constant current 算 VTH 的时候算这个值，这个值跟这个值，跟 constant 算 VTH 是这个值。这个是你会算出两种不同的，
可能我用10的6次方分负吧，两边分别去算。
对啊，你会算出两种不同的 EA， 但是一边的 EA 代表它的机制不太一样。
可是好奇怪，因为像我这个用某一种 EA， 它这个图看起来丢到面去就是长得非常的奇怪。
可是 NBTI 跟 PPTI 版就机制版就不太一样，所以就是反正就没有人说 PPTI 结果跟 NBTI 一样 consistent。你就在 PPTI 里面，你也可以有，说不定改变不同的 threshold voltage 定义方，你会发现不同的 EA。
所以这件事其实是合理的。
这是合理的，NBTI 跟 PPTI 版就不一样，对啊。
所以可能我在取电流法，我的电流选不同，可能导致我算出来的 EA 不同。
对啊。
但就是说，其实这都是
但是你要思考一下，因为你的电流法不同，代表你是萃取在更靠近 SS region 它那的时候，或是完全已经 saturate 的地方，所以两种的机制一定是不一样的。
就是都要看一种。
对，而且你的 VG bar 是一样。对，这个 stress 电压一样，但是这个量的 IDVG 的时候，你越下面一点，代表你的 VG 电流圈才刚打开而已，跟后面这个完全打开就不一样。对。
我可能再思考一下。
想问一下，
对，
就是因为我们以前学热力学的时候，他们说那个就是宇宙一个基本质像一个基本量，会是用 entropy 来描述说那个反应的进行。那老师这边特别是用这个 Gibbs energy 来提这件事情，是就是为什么要使用 Gibbs energy？ 因为它不是还会包含 entropy 的加减量。
没有，它这个只是去表示说，这 Gibbs energy 它用的时候想要得到最低最负。对，那只是一个 case， 一个是有跟 alcohol。那有跟 alcohol 的话，它会本身会改变它的这个 entropy 或 entropy。对，就是说，例如说这个油为什么它会想要最后会聚集在一起？那主要就是因为它这个 delta H 的关系。对，那为什么它这个 alcohol 会想要散开？这个可能你们材料比我还更懂，就是为什么这个 entropy 跟 entropy 会怎么影响到它的这个材料的。
所以但对于我们
半导体元件来说，我们就是这个嘛，对吧？因为你可以想看嘛，这个一定是高能量，因为它里面有加电压，对，它用一个东西强制分开，所以你很明显在 A 点跟 B 点就有很明显的这个 energy 的差。那系统一定想要往就是完全没有 energy 的情况下，让它的 breakdown potential 它就是达到一个 energy。
那我的意思说，假设就是因为假设我今天 entropy 增加，
对，
那 entropy 增加一定会导致这个 Gibbs 减少。
对。
假设我今天的那个 entropy 增加更多，就是这两个。
我只能说这个就很偏材料，你们可能比我还了解。我现在就是纯粹只是说这个情形它是在每个地方都有机会发生。但至于这个 entropy 和 entropy 这种材料什么机制会让它某一个增加，这个其实我觉得你们不用。对，那重点只是想要 illustrate， 我比较有兴趣是这个 case， 这个 case 是半导体常见的，就是你有加额外电压，你能量就变高，但它就会想要经过某种方法让它降低，变成最低的量。那这个东西也可以用 Gibbs 的 energy 这种概念去解释。对，
所以才会引入到说下面有就是解释。
对，所以这个也是一样，对啊，所以这个 location 的 energy 对。所以其实很多方法，它其实只是用不同方法去解释，但其实总归来说，你就算不了解这个，你也可以很直觉知道，你加一个 force， 它本来就会往右边。对，就算你不知道这个 energy 的存在，对，只是最终你会发现所有东西都是不同的。对。
好，谢谢。
但 R1到2为什么在讲技术的？
我看一下那边。
就是刚刚有抄这个公式，
对。
然后2到1刚刚看那个图是这个，
对。
不知道为什么这边要减对它。
就是反过来吧，就是如果说你今天假设你有这个 Orton， 他想要跳回去的话，他就是反过来的。
那个 barrier 它的高度的话delta G。
应该是说他这个 case 应该是这边把这当成delta G，这是delta G 键，就是反过来，就是把这设成delta G，然后这边是delta G 键 delta G star 减delta G。对，他只是假设说今天因为你不知道永远，它其实也会往左，会往右，对，但是只是说就看哪个现象大。对，就是其实你可以想象，其实就是这边啦，这边的话是往右是加，但是如果说它往左的话，它就减，就是你永远不知道它是往左还是往右。对。
好，谢谢。
probably you will join absolutely. Yes, yes. So I mean, after this, to finish it, finish this class and then finish the class. Okay. Because we will have some design section from the corporation last time. Yeah, and there's already some progress there. So even in the report from that, you also will kind of but I think at the moment you first to focus on the class, which is most important. Yes. Yes.
Even the course is matching. They are not ready to sign.
Yeah, but if he didn't want to sign it. Okay, but he's, I think they probably have to repay because this is from the communication, he's not familiar with this new degree. So I guess he's going to be against us. He's not familiar with this program, he doesn't have this new degree student. If you again, he's
So I have to around 3 to 4 years.
Oh really? You have to that
For this semester I have taken
yes.
if my credit will not be transferred, then I have to do the 4 years.
Okay. Let me know, but how many you can transfer? How many you can transfer? But how many you already can transfer?
I have already transferred 2 courses.
Okay.
But I am trying to transfer 2 courses.
Yes.
But the professors, some of the professors, they don't know.
Okay. Can you check with IC so please?
Yeah, actually I have made
Yes. And she said.
I raised this issue in the meeting.
Yeah.
Committee.
Okay. You will raise this. She will raise this issue.
Yeah, he will raise whenever the meeting will be over. And after that he will take me.
Okay, so let's further move on. So, as we have already discussed a lot the values, and then the acceleration factors. So this will be the kind of like a summary. What will be the temperature, and then influence our degradation. So as the temperature increase, the atoms vibrate high frequency and move further apart here. So first, the high frequency vibration energy means that the atoms bump into the space between the atoms more frequently with a higher energy. So imagine that you have the distance between the atoms. This is a case at the room temperature. And now you have one additional atoms in between. But at a high temperature, we can expect that the distance between the atoms is become larger. And also, at the high temperature, the atoms can have the easily vibrate because of a high temperature. This atom will get some additional energy, so then this atom will easily vibrate, and also the distance in between is larger, and therefore we can foresee this atom is getting more easily jump to the other place. So this is how this two sentence means here. First, a high frequency of vibration energy means the atom bump into a space between the atom more frequently with a high energy. And secondly, the space between the atoms are larger on average because the center to state spacing increases the temperature rise here. So that's we can understand from these schematics here. Therefore, the temperature accelerates the rate, and then that's the things why the temperature is a very important factor. And temperature has a twofold effects as described above. First, there's more energy driving the reactions or diffusion rate, and second, the reaction diffusion rate can place more easily because of a center to center results in the larger space from the atom to move through. So this is a sentence mainly described at this case. This is a case at a high temperature. So this is one way to understand why the temperature will accelerate the degradations. And furthermore, we have to introduce some additional concept here, and this one is what we call the load and strength. And we can consider that the reliability happen is between the strength and load. So first of all, we draw the schematic like in this way. In the one kind of one kind of the semiconductor products, so we can divide by the typical strength for this one can be described, show me here. And this, the top one, we can consider as a strength. And then the bottom one, we can consider as a load. So the strength that's in here, it means that the robustness, the quality, or the good state of one product, and the load, which is the one that has reached to the certain issues, and then with the time being passed by, the load will be always the same. But the problem is we can start to foresee the strength might have the degradation. And then also it's very important to understand that each strength and load has its own distribution, which means the load has this kind of a distribution, but also the strength has its own distribution. But with the time passed by, the strength will become weaker. And once the strength becomes weaker, we can see the degradation of the strength, like in this way. But load will be the basic state, so the load will be the same. But the problem will be the strength decrease. So we can start to foresee the top distribution start to overlap with the bottom distribution. And then once the overlap region get larger and larger to trigger the overall values, because once has overlap, that means certain degradation has been happened. And then once the degradation has achieved amount of the trigger condition, then we start to see the value of our device. So this overlap region reach to the certain condition, then we start to see the values. So this is another example, try to describe the things happen. And then in this slide is mainly to illustrate that we have to take into account of this distribution, because of this distribution, narrow and wider will also influence our stability. If you have very poor product quality, that means you have a very wide distribution, then for sure your overlap region may happen faster, and then the overlap region will become larger, and then you can see that you can expect that the reliability of your product is getting poor here. And next one, I also want to illustrate that's very important for this batch tube curve. Because of this batch tube, if you look at every semiconductor general introduction article, they always talk about the semiconductor has a lifetime, like this batch tube curve, which this batch tube curve is the same as a lifetime for everything in the world, including the human as well. So you can, this batch tube curve is plotting with considering for sure the x-axis will be the time. But now the y-axis, which is the value rate. So in general, no matter for what kind of a product, or even for the human, for all kind of the things in the world, that we can divide the value rate with the phase by 3 different phases. So we will have the first phase, which we can see in the beginning we have this very high value rate, but after reach a certain moment, the value rate is start to stabilize. So this is a phase that we call the infant mortality. We can use some very basic understanding example, not only in the semiconductor, just in regarding for a small baby. When small baby just come out to the world, in the beginning, they are so fragile and they have very high death rate, right? That's normally happen in the human as well. So that's why in the beginning we always suffering this infant high value rate. But once the baby start growing up, upper and upper, then they will start to have the way to survive. They getting more mature and their organs start to become stronger. So their value rate or death rate for the baby is still reduced. So this is exactly the same like a semiconductor product. When you first to produce a chip in the beginning, you have very high value rate. But after a certain moment, we will start to see the value rate will decrease here. But after reach this timing, we will reach to another phase that we call the useful life. So this is the second phases. If you talk about the human, so that would be the around the age between like the 5 to 70. That's our useful life. Our failure rate is quite low because our body is so good, and then we don't have any suffering the product of suffering any issues. That's the same like the semiconductor device. This is useful life that with a certain phase is very stable performance and without any reliability issues. But after certain timing, we will come out again with a high failure rate. This is a phase that we call the wear out. And then this is a moment we start to see the very high degradation. Like for the human, it's like after 70, after 18, you start to feel the degrade of your body, and then you start to see the death rate increase. So it's the same like the semiconductor as well. That we have started to experience after certain useful lifetime, then the semiconductor product will start to experience in the phase of the wear out. And because of the shape of this curve, that's why it's called the bath tube, just like the bath that you have in your shower room. So that's why it's called the bath tube here. So as I mentioned here, the early failure during the early life with the failure rate is high, since the product containing some of the growth or some manufacturing defects that cannot survive here. So that's a beginning, and that's why normally we need to have a certain screening process. So product must survive the certain tests of what we call the burn-in, and that's this kind of testing, which is stress at high temperature, electrical overstress, temperature cycling prior to the shipment. So this is one example of burn-in at 2400 hours at 125 Celsius degrees. So in this phase, because we have a lot of high failure rate due to the defect, due to contamination, due to a process issue, so we will have a screening process that can help us to remove this high failure rate product and try to finally find the very low failure rate product, and then we can start to ship to our customers. So this is a process that we call the screening, and then the test here is usually we call as a burn-in here. So one example, just to give you some of the example, let you have some more sense. For example, in the beginning, you produce 1,000 device, but some device suffering the very high failure rate because of defect, process, or blah blah, lots of issues. So we are first to have the screening process, and that's we do the burn-in. And then with this burn-in and screening, finally there will be the 100 weak device has been removed, and finally we can start to ship to our customer with a 900 good device. And this is a product that we can start to send to our customer. And then this product will start to in the phase of the useful life here. And that means that we have a 100 devices are suffering for the early failure. So that's why we need to have the screening or burn-in technique to identify which product has an early failure. 900 device is good, but the 100 device has a early failure. And then we have to apply this burn-in and screening. So finally, when we talk about failure, we have to always ask ourselves, this a very important failure triangle. This triangle is mainly help us to identify several key questions, which is when, how, and why. That's always very important for this failure triangle. So we need to always ask why the failures is happen, and when, because when is related to the time, related to the condition, and in the end how, what would be the mechanism inside. So these are the three important factors. And based on three important factors, we can always consider the several different preliminary identification. For example, in terms of when, we already knew that in the one certain product there is a three phase for this batch tube curve, where the first one is infant mortality, or this value is happening in the middle life, or this value is happening during the wear out. And also regarding to the why, is this value happening randomly? Or this value is following what we call the preordained. That means that there's some preconditions cause this or not. And the last question is most important, is how. For example, is this value is gradual happen, or it's a sudden, it's a catastrophic. With all these questions will help us to identify the reason cause these values here. So just let me to illustrate a little bit more what's the difference between the sudden and gradual. So in the case with TDDB of a dielectric, we often see the two different kind of curve. One is like this one. Another one is so this is a very often example. The first one just considers a sudden value because there's a one moment the current is increasingly very high. But the second case, which is a gradual, because we can see there is a noise of a current happening, and then the current is slowly increase. So that's why we can consider the gradual degradation. and to try to understand, because the most difficult part is for sure how to in the end to identify the reliability physics. And there's several approach. Normally we combine these all the approach together. The first one is the empirical approach. So this is mainly by we try to identify all the values, we try to collect all the frequency of the field returns, and in the end create a historical database to predict what is likely to happen to your next product. So it's basically we collect all the data, we save in our data sheet, in our database. Time to time we collect for 3 years, 5 years. Finally, we come up with some empirical approach that possibly we can identify the issue. So that's also very often used in the industry. And second one is statistical approach. So assume that each component has a certain failure rate, just like this one, and we need not know the physics of A and certain connectivity, and use rules of probability to predict overall reliability of the system. So basically, we try to use a statistic with a certain probability rule to predict the overall reliability of the system. So we know the failure rate for each one, but we don't know the physics of A, but we know how each component, how do they connect it with each other. So in this case, we can apply the probability rule to predict the overall reliability of system, even we don't know the physics. And then the last one, which is a physical approach. So we study the physics of an individual device to find out origin of A as a function of voltage, temperature, and use this in the statistical model and compare with the empirical results. Basically, that we study the physics inside this component A to understand what would be the physics cause this reliability issue. So these are the three general approach to understand the reliability physics. And in this class, we mainly focus on the statistical and physical approach, because the empirical approach, you need to have very dedicated database. You need to collect the time to time over several years. But in this class, we mainly illustrate how we partly use a statistic way, how we analyze the physics inside in the end to elucidate what will be the physics mechanisms that lead to such a instability. And also, there's a very important concept that we call the margin of the safety. So imagine that this is a string. You have one side, and you try to pull this string from these two opposite sides. And then when you try to pull the string, then you can analyze the strand on this string, and then by consider the stress where you apply. So then you can first to expect that it could be you apply the stress a larger and larger, then your string will suffering a higher and higher strain. So this is initial phase, where is this one, and then the second, the yellow one will be here. But after certain one critical condition that we can foresee, the strain is go very high, and that cause the values here. So this is the moment of the value point. And with this kind of the illustration, we can first define below this critical point, everything is safe. So that's why we call this region as a safety margin. This is a very simple case when we consider we just pull the string until the breakage, and then we tell our customer that no, you cannot break it. Pull such large in the stress, you have to limit yourself with a certain stress. But this safe margin is also very important for our product, because in the end we need to define what will be the safety margin for our semiconductor device. You have to tell your customer that your margin will be maximum voltage you can apply, which is less than 10 volt, the 10 gate voltage, or less than 20 volt in the drain voltage, and then you cannot operate your device beyond 150 Celsius degrees. This all the safety margin in the end gives the customer that what would be the recommended bias condition that we can make sure our device, our product can operate stably. So when we talk about the statistic reliability, then we have to introduce the two concept, but which I believe you have been already learning this from the high school. This is what we call the series system or the parallel connections. So in the case with the series system, we just consider that we have the two independent components that being connected in the series way. So you have a component A, you have a component B, and connected with each other in the series, right? So that's why we call the series. And then the value probability for the component A, which is P A, and then the value probability for the component B, which is a P B. And for sure, we consider the series system, the system value probability, which will be the product of PA and PB, right? So that's a high school probability. So this is nothing very difficult mathematics. This is what we already know, that you have a two independent event. You connect this event in the one series way, then the overall probability will be the component A times the component B. That will be overall system value reliability. And another is what we call the parallel system, which is also very simple. We have the two components in place in parallel with each other, and each one has its own value probability. So we're just connecting in this way. So then the system continue to operate until the last unit falls. So if this is fail, the system can still operate, and system will be only fail if all these two components fail, and then the probability can be expressed by this. So this is something that we would need to know when we analyze the reliability. This is between the series and then the parallel connections. And this is a general equation for this one. Then you can try to look up by yourself, so we won't spend too much time on this. And there's also some YouTube that you can watch out. It's very short, just 5 minutes. It's very easy to understand what's the difference between the series system and then the parallel system. So finally, the conclusion from this chapter, which is first one, we talk about some reliability core principles. So first we define what is the reliability. It's a probability of the operating a device, a system for a certain time under defined condition without failure. So that's a reliability. And how do we determine reliability? We have to consider the specific condition, statistic nature, and time dependency. And what in the end will cause a failure, which can be complete breakdown, gradual degradation, failing to meet certain performance spec. For example, 20% of the R increase, 20% of the threshold voltage shift. And there's a certain quantitative matrix for the NTTF, NTBF, T15, T16.3, and T1, and also the failure rate. And we very often use the batch tube curve to understand there will be the 3 different phases, which is early failures, stable operation, and wear out failures. And we also discussed what would be the failure physics and practical implication. For example, the difference between the failure modes and mechanism. The modes is related to the observed symptom. The mechanism is related to the physical root cause. And we have to understand there's always a transition from the reliable to fail. This is driven by thermodynamics, enabled by kinetics, and then it's very important to understand there's a arenas consideration with activation energy plus temperature. And we also talk about the diffusion, charge trapping, and there's a certain related to electron migration, TDDB, or hard carrier effect. This is all that related to the atomistic process, and the exertion factor with a high temperature stress. And sometimes we also consider the voltage and humidity biasing. And there are 3 general ways for approach for reliability: the empirical, statistical, and physical base here. And so reliability engineer bridge the physics, bridge statistic probability with a physical degradation mechanism. So a robust reliability program combines acceleration testing, physical-based modeling, and system-level design to ensure the long-term device performance. So this is a very key result that normally when we do the reliability study, we do the acceleration testing, we do the physical-based modeling analysis, and in the end, we will also propose designed in the end to improve the reliability. In the end, the goal is to ensure the long-term, stable, good performance. Okay, so that's the end of this chapter. So then we will move to the next one, which is still in the pretty fundamental. Just tell you that the basic. This is more related to the semiconductor device, how they operated and fabricated. First of all, what would be expected to learn by the end of this chapter? So you will be able to explain the fundamental semiconductor physics. Of course, some of you are currently following the semiconductor physics device. Some of you have already followed, but basically we will still quickly go through which is more important related to semiconductor, related to crystal, dopants, electron holes, and energy band, because this concept we will need it for later reliability. And also we will you will be able to understand and analyze the device operation principle between the junction and then the MOSFET. And then also when we talk about semiconductor physics, we have to always mention about the quantum mechanics here. Interpret the quantum mechanics concept. But you don't have to worry, because we will use the most easy way to explain the quantum mechanics, and we don't need the not that very difficult concept. We only need a very easy one. That's enough for us. And then also we also just a brief to mention about certain fabrication process. And of course, each semiconductor has their own unique fabrication, but the general fabrication is always involved the wafer preparation, oxidation, photolithography, thin film etching, doping, packaging. That's a general fabrication from the beginning raw material until the device in the package level. And then also we will describe a little bit about the planar MOSFET to the FinFET. So first one, what is a semiconductor? So the semiconductor is a material that has interesting conductivity between the insulator and then the conductor. So then first we have to be aware of that in the materials world, there's already the material that has what we call the insulator, which has a very low conductivity. But on the other hand, we have the material that has a very high conductivity that we typically call as a conductor. So for example, the conductor could be copper, aluminum, and so on. And then the insulator can be glass, diamond, and something like this one. That's a plastic. These are all the insulator. And semiconductor just has a characteristic just in the between the conductor and insulator. So now you can see that one of the most powerful performance for semiconductor is we have the very wide range of the conductivity. You can have a conductivity very conductive like the metal, but you can have the conductivity very close to the insulator, and in between we have this huge variation. This is from 10 to minus 8 to 10 to 4, so we have a 6 order difference, and everything here can be easily controlled by the additional bias. So that's why this semiconductor is very powerful, especially the silicon, which nowadays still will be the dominating material. So the semiconductor can have the very wide range of conductivity that gives us a very good capability to control the conduction of the electron from the very wide range. And then because of this, the capability to control the conductivity, so we can use this semiconductor in the end to make it as an electronic switch. So the typical in the nowadays we are living the world with lots of the mechanical switch, like you turn on the light, you turn on the many things still rely on the mechanical switch. But the problem for mechanical switch is that still too slow. But the ones we can make it as an electronic switch, then we can make it very fast, and we don't need a lot of power, and we can also, most important, we can make it very small that can integrate into many applications. So when we talk about the semiconductor, for sure that the raw material is silicon. As we already say that the most important structure for the semiconductor, which is a structure where we have the source and drain, and we have the substrate, which is a P-type silicon. In lots of cases, we have this one as a raw material, and on top of this we have the dielectric, and then on top of this we have the metal, so this will be, but we not only have the metal in the gate side, we also have the metal in the source region. We also have the metal in the drain region. So these are all the metal here. So this is a gate, source, and drain metal. But the semiconductor cannot only be rely on the semiconductor itself. Actually, it's a semiconductor device is a combination of the conductor, semiconductor, and insulator. For example, in this structure where we have the MOSFET, for sure, with starting material is a semiconductor. That's our substrate. But we also need a conductor, which is our gate source drain metal. And also, we still need the insulator. Which is our dielectric. And in lots of cases, we use silicon dioxide. So then you can see that a good semiconductor device is actually a combination of the good semiconductor material, good conductor material, good insulator material. So with all these three, finally we can make it as a very good semiconductor device. And let's go from very fundamental to understand what would be the material that possibly can be used for semiconductor. And for sure, we will look at these materials from the periodic tables, and we realize that in the periodic tables that the group 3, 4, 5, which are the species that can be used for semiconductor, especially the most important one is in the group 4, where we have the silicon here. So the semiconductor made by only the silicon or germanium, that we call as an elemental semiconductor. But the semiconductor that made by the several species together, where that we call the compound semiconductor. For example, the gallium arsenide, which is very important and is already commercialized that you use for your daily life. And also we have other compound semiconductor, for example, the indium gallium arsenide, or aluminum gallium nitride, or silicon carbide, and so on, or silicon germanium. These are the nowadays very important compound semiconductor. We just try to make the group 3 combine with the group 4, or we try to combine the two species in the group 4, and then we can make it as a compound semiconductor. And one of the cool things for semiconductor is we can have very wide range of conductivity. But how we can make it a very wide range of conductivity depends on how we can be possible to dopant in silicon. So the dopant means that we give this piece of material additional atoms, and then we can dramatically change their conductivity. So that's why the dopant in the semiconductor is very important. And in general, we can divide the two different dopants here. So one is what we call the donor. And the donor is a semiconductor that is a species that we can turn the semiconductor into the N-type semiconductor. So imagine that you have the silicon atoms in the lattice. And as we all knew that in the outer shell of silicon, we have the 4 electrons. And because of the 4 electrons and connect with another 4 electron, and we can form the bonding here. But if we try to place a group 5 in the middle, so group 5 means that this material, this species has a 5 electron in the outer shell. So which means, for example, we use arsenic, and arsenic has a 5 electrons, 1, 2, 3, 4. But now we got the 1. Additional 1 here, but this additional 1 didn't bond with another atoms nearby, so this additional 1 becomes the free electrons. So that's why the arsenic can introduce electrons and in the end create the N-type silicon material. And because of arsenic is one who donates the additional electrons. That's why we call this as a donor, because he donates the additional electrons here. So on the other hand, similar things we can consider that again we have a silicon and then we all knew that we have the 4 electrons here. But now if we consider that we pick up the group 3 material where we are interested in use of boron, but the boron only have the 3 electrons in the outer shell, so which means we have a bonding here, here, here. But now we got the 1 additional empty place here, and this additional empty place will be able to accept 1 electron from other. So if you have an additional 1 electron, this electron might be able to flow into this one. So because the boron introduces 1 empty space that can possibly accept 1 electrons, and this phenomenon of the accept 1 electron also can be considered as a holes. Because you in this place you have 1 electron come in, that means this place has a 1 electron missing, and the hole will be start to moving from here. So you can imagine this is also the whole movement in the end. So the boron introduce holes and in the end create a p-type silicons, and because of boron can accept 1 additional electron from the other place, so that's why we call this as an acceptor. So in this class, most of us is not the native speaker. So when I was starting the semiconductor physics, if you try to look at some Mandarin textbook, they call this as 载体、受体, however, it's very difficult to understand, and then sometimes also get confused that why use a donor or acceptor. But I hope now you can understand that the donor acceptor just because of this kind of reaction just related where they donate 1 electron or they accept 1 electron. That's why we call this as a donor or acceptor here. So that's why we can make the silicon material where has a N-type doping or P-type doping. And then reality, we will actually, if you consider the structure of the MOSFET here, normally we have the N plus in the source drain, we have a P minus in the substrate, and this plus suggests that we have the high doping. But in the semiconductor world, we don't call this high. I don't know why, but just very get used to, we call this heavily doping. And then in contrast of the heavily doping, this minus we don't call as a low doping, we just call as a lightly doping. So that's why if you look at the Mandarin textbook, they call this as a 重掺杂, 轻掺杂. But in anyhow, just try to describe this high doping, low doping, but we just don't use a high and low. We just use a heavily doping, lightly doping as this term. Okay, so probably we will stop here, and then we will continue the rest in the next week. So if you have any question, you are feel free to come to talk to me. So we will see each other next week.